Julie Simpson. I'm a coastal ecologist here with the MIT Sea Grant Program, and it is my pleasure to moderate this morning's session, where we have some great speakers. I wanted to say one quick note, which is in response to the earlier question about models and whether or not they take into account inundation and structural aspects of the environment. The answer is some do and some don't, and we're having our next session after this one is a bunch of different modelers presenting their work, and you'll have the opportunity to ask them directly and see what exactly their models focus on. So hopefully we'll have an entire session to answer that question. Quick organizational note, we're having 3 speakers in this morning's session, and after each speaker there'll be a short amount of time for questions directed towards that speaker. You can use the microphones or wave, and Arlen, are you here? Arlen can hopefully bring the microphone to you. At the very end, we're hoping to have 10 or 15 minutes for an entire panel discussion. The whole panel can sit up here. And if you have questions for the whole panel, please write them down on the index card that should be in your folder, your packet that you got this morning. And if you write them down and at the end of each talk, kind of wave them up in the air, pass them to the left, and Arlen will be able to pick them up, and then we can sort through them and give them to the panel for the entire panel discussion at the end. All right, our first speaker today, I'm very pleased to announce, is Cameron Wake. Cameron is at the University of New Hampshire Institute for the Study of Earth, Oceans, and Space. He is the Josephine Lamprey Professor in Climate and Sustainability at the Sustainability Institute, and he is the Director of Climate Solutions New England, which is a group up at UNH, which is organized to promote regional collaboration towards the goal of greater energy self-reliance and weather resilience to promote prosperous and sustainable communities. So, small goals. Thanks very much, Cameron. Welcome.
Thanks, Juliette, and thanks for inviting me today to talk about climate change, specifically across the Northeast. I'm hoping I'll get through these so that I can answer a few questions as well. But I want to start by saying that climate change, I think, is the greatest challenge faced by humanity in the 21st century. And the reason is that climate change makes every other grand challenge more difficult. So if you're concerned about food security and childhood hunger, well, it's going to be made more difficult by the issue of climate change because of the excessive heat and droughts and flooding that are going to occur in the tropical regions and temperate regions. That's going to make it more challenging to grow food to feed a growing population. You might think that national security and reducing conflict around the globe is a grand challenge. The Pentagon recently came out with its quadrennial defense review that clearly identifies climate change as a threat multiplier, one that's going to make social tensions and poverty and environmental degradation and political instability actually enhance, which is going to continue to enhance conflict. You might think that the reduction, species extinction and biodiversity is the grand challenge. And we are now in the midst of the 6th great extinction, in part because of land uses change, but now ever more frequently because of climate change. Or perhaps you're really concerned with public health as the grand challenge. And public health is certainly going to be made more difficult as a result of increases in air pollution driven by warming temperatures, increases in pollen, increases in vector-borne disease, in addition to increases in flooding. So with that framework, I really want to share 3 things in my 25 minutes up here with you about climate change. The first one is climate changes. Climate always has changed and climate always will change. The only difference today is that there's an overwhelming and ever-growing body of scientific evidence that shows that humans are the main drivers of that change. And in fact, 97% of climatologists who publish in the field have come to the independent conclusion on their own that humans are the main driver of climate change. It is time to listen to the science community and start figuring out how we go about solving this problem. I am by training an ice core paleoclimatologist, so I want to show you one suite of ice core data. And this is a record from a combined Vostok and Dome C ice core from Antarctica. And what I really want to highlight is this delicate dance between carbon dioxide and temperature. So we measure carbon dioxide in the bubbles in the ice cores. Those are the bubbles. That's a thin section of an ice core. Those are the bubbles right there. So we extract that gas and we measure the carbon dioxide. Temperatures measured by looking at the stable isotope content of the ice. And you can see this really significant relationship. Higher carbon dioxide, right? Warmer temperatures, lower carbon dioxide, lower temperatures. And it's not that one drives the other, it's that they're in a delicate dance. And for an environmental scientist, this graph is as beautiful as a Mozart symphony. It's as beautiful as a Van Gogh painting, or it's as beautiful as the Boston Red Sox winning the World Series, right? This is a really well-documented record that shows this intricate dance. And enter human beings. We start monitoring carbon dioxide in the atmosphere in 1957 in Mauna Loa. And you can see that as a result, primarily of the burning of fossil fuels, which provides us with energy, byproduct of carbon dioxide, we have raised the level of carbon dioxide in the atmosphere an equivalent amount to what we see during a glacial interglacial transition. And if we're not careful, we're going to end up where we're going and end up with carbon dioxide at 800, 1,000, 1,200 parts per million by volume. That's going to result in catastrophic climate change. Bringing you back up to the present a little bit more, Anthony's already shown you this graph, right? This has really taken the scientific community by storm, the rapid disintegration of Arctic sea ice at the end of the summer. We always thought it would go away, but it's going away much more quickly. So you can see in the yellow line here, the average over the course since 1979, then you can see the significant reduction in sea ice at the end of the summer. Why do you care? It's the air conditioner for the northern hemisphere. It's white, so it reflects incoming solar radiation back out into space. When you remove that white surface, that dark ocean absorbs way more of incoming solar radiation. It warms up the water, making it much more difficult for that sea ice to form. It's likely going to disappear in the next decade or two, and it's not going to come back. I mean, it will come back in February when there's no sun in the Arctic, but end of the summer, we're going to have an ice-free Arctic, and we need to start thinking about the ramifications of that. All right, moving quickly to the Northeast. I'm going to talk a little bit about how climate has changed and then how climate might change in the future. And initially, looking at past trends, we use data from the U.S. Historical Climatology Network. These are our best long-term meteorological stations. You can just Google them and find out a lot more information. But there's 137 of them across the Northeast, which is New England, New York, Pennsylvania, and New Jersey. At least that's how I'm defining it. So we've looked at a lot of different trends in all the different seasons. And what we really see is that it is our winters that are warming the most rapidly. So you can see in blue the year-to-year variability. This is an area-weighted mean for the Northeast. You know, if you don't like the weather one winter, just wait, because next winter is going to be different, right? Lots of variability. But there's clearly some long-term trends on here. So you see in the red line just a linear regression put through that data set. And you can see warming on the order of 2 to 3 degrees Fahrenheit over that time period. But what's more dramatic is the warming that we've seen since 1970. And we've done this analysis lots of different ways, lots of different sensitivity analysis. The rate of warming has increased substantially so that we've seen 4 to 5 degrees Fahrenheit warming over the course of the past 4 decades. Right, we've also looked at precipitation. Overall, it's getting slightly wetter across the Northeast. This is good. Water is likely, in my humble opinion, to be the most critical resource in the future, and we're likely going to have lots of it. I'll talk about that. You'll also see on here our last really big drought happened in 1965. And that was actually a drought that affected most of New England, a little bit of New York, but was fairly significant and began a series of not quite, but close to water wars. And we have an experience. We had a little drought in 2001, but recently we've really been blessed with water, and I'll come back to that. Unfortunately, more of our rain is coming in fewer events. So this is just site-specific information that I've pulled together for New Hampshire that I wanted to share with you, because it's really important, because precipitation is so heterogeneous. It varies spatially so much. It's important to look at specific meteorological stations. So here are what I'm calling extreme precipitation, greater than 4 inches of precipitation that occurs in 48 hours. All right, and these are events per decade. So up here, you've got Durham, New Hampshire, right? About one event from 1963 to 1972, and then we march along to the most recent decade. You can see in Durham, New Hampshire, we have had a 10-fold increase in extreme precipitation events. Same at Lakeport, New Hampshire. Nashua, New Hampshire has gone from a couple of events to 15, and Mount Sunapee has gone from 1 to 7, right? This is particularly predominant across coastal areas of all of New England and other parts across the Northeast. And it's a real challenge. So precipitation's going up, but more of it's coming in fewer events. What are we going to do with that water? In some ways, that increase in precipitation and fewer events is reflected in this graph, which is not a climate graph, but it does reflect climate change. This is the amount of money that the states across, this is New England in this case, have asked from the federal government as a result of presidentially declared disasters and emergency declarations, right? And you can begin to see that there's a significant change starting in 2003 and then in 2010, right? You can see the impacts of Sandy and Irene as well in the end, right? So not only is climate changing, but we've also put our infrastructure in areas that are particularly vulnerable to a new climate normal, and we're beginning to see the results of decades-long work on that front. So my question for you is, are you ready for the next storm? Because we have had a series of storms that have no precedence, really, in terms of our collective memory and the way that we design. This one is perhaps the most interesting, Snowtober. Back in October 2011, we had a foot of snow in New Hampshire anyway. On October 30th, when the oak leaves were still on the trees. All kinds of trees fell over the power lines, millions and millions of people without power for many days across all of New England. When the CEO from Public Service of New Hampshire was dragged up to the State House, they said, "Were you prepared?" He said, "I was as prepared as we could have been, but we've never had a storm like this in the past." As a result, PSNH and Unitil and many other companies are now cutting trees down around power lines everywhere. I'm sure you've seen it in your neighborhood in response to this storm. We've had a whole series of floods. This one is Newmarket, New Hampshire, back in 2007, but we had flooding in 2006, 2005, 2010, right? Were we ready for those storms? Certainly not by the amount of damage that was done. And then clearly, Irene affected a lot of areas, and particularly Vermont, and then Hurricane Sandy. So how do we start thinking about building our infrastructure and making our coastal cities resilient in the face of not being able to use the historical past as an analog? So what I'm going to share with you is results not from these reports, but these are a series of climate assessments that we've just written for the state of New Hampshire. So if you think about, you got the Intergovernmental Panel on Climate Change Global Assessment. We now have the National Climate Assessment that's particularly for the nation. So we're now developing a series of assessments for particular states across the Northeast and New England. And so these reports can be downloaded at our climatesolutions.org website and provide you with all the background methodology of the figures I'm going to show you that focus on the Northeast. First and foremost, how is our climate going to change in the future? I started off by saying humans are now the main driver of change. Once you absorb that, you understand that the future climate is literally in our hands. Right? It's the decisions we make over the course of the next decade about how we use and how we produce energy that's going to determine our climate at 2100, right? So the bad news is we're changing climate, right? And it's going to get worse if we don't do something about it. The good news is we're changing climate, so we can actually do something about it. But as we look out to the future, the biggest uncertainty really deals with how much greenhouse gas human activities are going to put in the atmosphere. Although a close second now is what Antarctica and Greenland ice sheets are going to do. So in order to deal with this uncertainty about human activity, is instead of trying to predict the future, scientists have developed a range of scenarios. And again, Anthony spoke a little bit about this. These are from the special report on emission scenarios. These are from the old IPCC from 2007. But the new scenarios are very similar to these. So we've chosen just to use a high emissions scenario where population grows to 9 billion by the middle of the century. The developed world spends considerable resources to bring the developing world out of poverty. But that happens primarily through the burning of fossil fuels. So we see our fossil fuel emissions triple, and that leads to 1,000 parts per million carbon dioxide in the atmosphere. Conversely, on the low emission scenario, same population and sort of global resources scenario, but we invest in energy efficiency and renewable technologies. The developed world drops its emissions. The developing world continues to grow its emissions, but by the middle of the century, we're all reducing our emissions. And that ends up sort of 450 parts per million with climate change, but climate change we can actually deal with. So the next thing, so all these global climate models were run sort of in support of the Intergovernmental Panel on Climate Change effort. We get a lot of these results, and what I've done is worked with a colleague, Catherine Hayhoe at Texas Tech University, to downscale that information so that we get much more site-specific information across the Northeast. So here's the grid cells that come out of a typical global climate model, so we downscale that. And we've used 4 particular models. You can ask me why we use those, but they're really well reflected in the scientific literature. They have a long history. They had results for the B1 and A1FI scenarios. And probably most importantly, they do a good job across the Northeast at recreating the climate change that we have already seen. Catherine Hayhoe and her colleagues have developed a new statistical downscaling technique called asynchronous regional regression model. And so in the past, what we did to connect a model output to an observed temperature, right, is we plot the data, that's in the black dots there, and we put a straight line through that data and say that's the relationship. So when you get a model output, you statistically downscale it to an observed temperature at a grid cell or a particular station. So what this new system does is actually, you can see these gray lines are breakpoints. So you put a series of regressions through these, but you break it up. And so that the resulting short segments actually much better represent the relationship between the model output and the observed temperature, so that we can better understand, especially at the tails here, right? You can see it's very much like an S-curve, and that we're capturing that. I should also say, right, all models are wrong, some models are useful. This isn't perfect, but it's actually a really valuable tool for envisioning climate change in the future. And so we actually downscaled this. We did do it to a grid, but Catherine also did it to 469. Now we're using GCN stations, Global Historical Climatology Network stations that have daily data. So 469 across these for temperature. You can see we have really good spatial coverage for the entire region. All right, so how our temperature is going to change. Here we're looking particularly at summer maximum temperature. We've already heard the importance of that. So this isn't the highest temperature in summer. This is average temperatures, maximum temperatures during the summer. So 3 months during the summer. So a couple points that are really important here is that the high emission scenario in red and the low emission scenario in blue, right? By 2050, there's very little difference between the high emissions and low emission scenario. Right? There's not a lot of uncertainty on how much summer maximum temperatures are going to warm over the course of the next 30 to 40 years. Right? They're very similar no matter what emission scenario we follow. So let's start figuring out how to adapt to that. Let's not build any more buildings with black roofs in Boston, for example. Conversely, under the high emission scenario, by the end of the century, we see warming on the order of 11 and 12 degrees Fahrenheit for the entire region. Right? That's a regional Northeast average. Under low emission scenarios, we stay pretty much at those 2050 levels of an increase of about 4 to 5 to 6 degrees Fahrenheit. How's precipitation going to change? You can see here that they're really, oh, do I have temperature there? Oh, sorry, minimum temperature. Right. So you don't see a big difference between the changes in minimum temperature under the high emissions or the low emission scenario. Right? Our winters are going to warm. We're going to end up losing a lot of our snow. It's going to be much more challenging for winter recreation. Perhaps a more significant adaptation is cold winters actually reduce a lot of the pests and weeds and insects that we don't appreciate here across much of the Northeast. So as those winters warm, we're going to have to deal with more of those. And enemy number one here, I think, is Lyme tick disease, but there's plenty of other concerns. So a number of days hotter than 9 degrees Fahrenheit. You've seen sort of different versions of this, right? But very similar story, no matter what type of different statistical downscaling model we use. The historical record here, right across the region, we sort of had 7 to 8 of these, averaged across the Northeast. By the end of the century, we see something on the order of 50 of these across the entire region. So more than a five-fold increase in hot days. Under the low emission scenario, those go up to 20. And this number would certainly be much higher at those cities in the southern part of the region and less in cities in the northern part of the region, something that we need to start preparing for. We did the same downscaling for precipitation. It turns out there's many more GHCN stations for precipitation, 850 stations across the region. So once again, we've got the region covered pretty well. When you look at precipitation in the future, you see no difference between the high emissions and low emission scenarios, right? This is actually good news for the Northeast. We are going to have water in the future. All right, and as the Southwest continues to dry out, I imagine there's going to be a lot of people who are very thirsty who look to the Northeast and say, hey, they have water, let's move there. Unfortunately, more of that water is going to continue to come in fewer events. So when you look at this precipitation events greater than 4 inches in 48 hours, again, this is the ensemble mean from those 4 GCMs. You can see on average across the entire region, we had about 4, right, with lots of spatial variability associated with that number, but you can see an almost tripling of the number of extreme precipitation events. And you can look at extreme precipitation many different ways. These are really looking at the biggest storms, right? But more rain in fewer events. So we're going to have water, but we're going to have lots of it in big storms, so we're going to have to figure out what to do with it. If you want to look at sort of that spatial variation across New England, I didn't have a plot actually for all of the Northeast, but you can see in the key down here, right, these big blue, greater than 19 more events per decade difference between the historical record and the end of the century. You can see pretty much a huge bullseye down here, right? 11 to 15, 16 to 19, greater than 19. And that's where primarily most of the development is across our region, right? How do we make, as Nancy Gerard has mentioned, more impervious surfaces, more storage? Do we pump this stuff back into the ground? How do we actually preserve this water so it's not flooding our regions? So paradoxically, lots of rain, right? We're also going to get more drought. And the reason is because none of the statistical or dynamical downscaling that we do shows an increase in precipitation in summertime. We see summertime precipitation increasing slightly over the next couple of decades, then remaining relatively flat. You combine that with increases of 9 to 10 to 11 degrees Fahrenheit in summertime, and you get way more evaporation, and droughts defined for a balance between inputs and outputs, right? Soil moisture. So in addition to more floods, which are going to happen in the fall, winter, and spring, we expect to see more drought as well. And this is a bit of a complicated picture, but here's the frequency of drought from 1961 to 1990. You can see lots of greens in there, right? 10 to 15 droughts per 30-year period. We tend to have a drought every 1 to 2.5, 1 to 3 years across New England. Short-term drought in this column. Under the high emission scenario, by the end of the century, you can see almost all of New England is actually pink. Right? 30 droughts in a 30-year period, a drought every summer, and you can see an increase in a drought across much of the rest of the region. Under the low emission scenario, you don't see that substantial change across much of New England, but it is something we're likely going to have to deal with. You've already seen this plot, sea level rise from the National Climate Assessment, right? The proxy records, the tide gauge records, the satellite data, and then this uncertainty going forward. So their advisement was, you have to think about 1 to 4 feet of sea level rise. Paul Kirshen, who's here today, and I have just, and some others have just provided some advice to the New Hampshire legislature, and we've said, if you have very little tolerance for risk, you need to start thinking about building for 4 feet of sea level rise at the end of the century. But you also have to maintain flexibility so that if we follow that higher emissions curve, right, up here, that you are able to adapt to sea level rise as it rises more rapidly. And I can tell you, Greenland and West Antarctica are starting to behave very differently. There was a seminal set of papers that came out just a few weeks ago that talks about how it's inevitable that the West Antarctic ice sheet is going to melt. We just don't know how quickly. It's not going to happen tomorrow, next year, next decade, even over the next couple of decades. We have time to react. But if there's one thing I could leave you with in terms of building, is that we can no longer actually build to a specific number. There's uncertainty about the future because there's uncertainty associated with what human beings are going to do, and there's uncertainty with, in some aspects, how Greenland and Antarctica are going to react. So it's really critical to integrate that flexibility into whatever we do in the future. All right, so I'm just going to finish up with a couple of examples here, because so often climate change has been presented as this problem we have to deal with. But I want to argue that actually climate change is the innovation opportunity of the 21st century. If you really begin to understand the new risks that we are facing, it requires a new way of thinking to solve this problem, and one that I think we can address if we choose to address it. We just haven't done so yet as a society. So let me give you a couple of examples. One is, how do we invest in our infrastructure? So much of what we've done in the past is we've looked for actually governments to assist us. There's just not enough money in state and federal governments to deal with this problem. right? Add up the numbers sometime. Massachusetts can't even rebuild the seawalls that are crumbling, let alone begin to prepare for sea level rise, right? So there's actually a whole range of different new instruments that are being developed in ways that people can actually invest in their communities and expect a reasonable rate of return. This is very popular with energy efficiency, Green Bank in Connecticut, Community Loan Fund in New Hampshire. There's lots of examples of this. But how is it that we can invest our money in our communities, our retirement funds, expect a decent rate of return, and help solve problems in our community instead of having our dollars go up smokestacks in China? There's a large, slow money movement happening, and it needs to happen faster because that's where the capital is going to come from to transform our cities. We've also had a wonderful couple of decades across much of the Northeast of land preservation. Public-private partnerships, federal government, state government, private entities, nonprofits like the Nature Conservancy and Land Trust. And I would argue we need to think very seriously, not about preserving current salt marshes, but where are the salt marshes going to be 100 years from now? Preserving those salt marshes will provide considerable resiliency for coastal communities, but we're thinking about what's there today, not about what's there in 100 years, right? We need to allow our salt marshes to migrate inland. A lot of those areas have been built already. Let's figure out how we preserve the rest of them, because there is no more cost-effective way to protect our communities from storm surge. And then last but not least, I would argue that we really need to think about how we collaborate more effectively together. I put this image up here because this is one of the groups I'm involved with, the Coastal Adaptation Work Group in New Hampshire, right? Federal representatives, state representatives, local representatives, planners. But we have enough institutions, we just don't work well together. It's not about, MIT working with other universities across Massachusetts and the Northeast. It's about universities working with federal agencies, working with state agencies, working with municipalities, working with nonprofits to figure out what the problems are. We need whole new levels of collaboration. And in fact, I think we can look to the New England tradition of town meetings to figure out how we might go about doing this. It's not perfect, but it works. We just need to expand that out from municipal decision making to a much broader audience. And last but not least, we're trying to do this in part at UNH through a National Science Foundation grant called ICINET, Infrastructure and Climate Network. You've already seen this picture twice today. I put it up here because this is our colleague, Charlie Hobson from Maine DOT, sitting beside a culvert. He's sort of the culvert king in Maine, really encouraging to build more culverts. But we're really trying to figure out how we get engineers and climate scientists to talk more together, to work more together. And I can tell you it's a significant challenge, but ones that we need to take head on. And now we need to involve a whole other range of individuals as well. So I'll stop there and be happy to answer any questions.
Probably two quick questions.
Is there a minimum size laboratory, physical laboratory that you can create where we can test some of the hypotheses that we want to put forward? Let me explain to you. What I think we're missing is there is really no evidence of the reward. In other words, if I do certain things, what do I gain? In other words, we keep on saying we want to do this, A, B, C, but I never see any benefit at the other end. So is there an experiment that we can perform? And this is now looking at a real physical city where I can convince, or you can convince the mayor then to really participate. You make predictions, and then I live with your predictions, to show that there is a benefit?
So I think that's a great question, and I think it's a huge challenge because the change is happening in our communities now. We're doing the experiments in our communities, and it's pretty hard to identify that community as a control. So the tools that we have are models, right? And you'll hear more about very specific modeling in the upcoming talks. But I think it's a real challenge. And so I would say it's not about any one community. What we need to do much better is engage in working with existing communities and really think about these innovations that we develop, whether they're about adaptation or mitigation. Think about them as experiments and not solutions. so that we actually do something and then we go back in and analyze it. But I don't think there's any one entity that we can really test, because Boston Harbor is different from New York Harbor, is different from Portsmouth, and all of those are going to require different solutions. And there's also many different scales in that, Boston, you have somebody like Nancy Gerard who thinks about this stuff. In Rye, New Hampshire, they have a volunteer planner, right? So they don't have the resources. So I think we need to think about all of our communities as sites where we do this experiment and this testing.
Yeah, but I've learned from bitter experience. You better start with one. In other words, yeah, sure, you mentioned it also before that you want, collaboration among many things. Yeah, we do collaborate, but there is really no metric, nothing. Nothing at the other end that I can hold myself accountable. I've done this, now here's my reward.
So we've done that in the coastal adaptation work group, especially in Seabrook, Hampton, and Portsmouth. So we've set some metrics. I think there's a whole, Vermont thinks about infrastructure entirely differently now because of Irene. So I think I would argue there's examples out there, and we need many more of those examples. The reward's a good one. We have to change academia, but that's another, right? We have to stop being rewarded strictly for the papers that we publish in peer-reviewed scientific literature. And we need to be rewarded for actually helping solve societal problems. Not either or, but both.
Traditionally, science leads engineering most of the time, but then the relationship is not very good. What does University of New Hampshire is doing in terms of bringing those together? Science needs to reach out and then have input from everywhere, and it can't lead the effort by itself. So that way, whatever the solution you can come up with, it's a better collaborative. And I'm just giving a small example. It's a lot more input, and you add politics to it and so on and so forth. But what are you doing specifically in terms of when you're doing data analysis and all this stuff, reaching out and then getting, engineering communities and other involved in the part of the initial decision-making process, rather than just you doing it and then them following through?
Right. So excellent question. It's turned out to be way more challenging than we thought when we wrote the proposal. 2 years in, I would say we bring together engineers and climate scientists who have an interest in this. And what we found was that at the beginning, we continually talked past each other. So let me give you one example is when you talk to an engineer, so I'm not an engineer, but I've learned this about engineers. When you talk to an engineer about a conservative design, that is a design that is going to withstand anything that can be thrown at it. When you talk to a climate scientist, talks about a conservative estimate, that's one where we lowball it so that we're very sure that is going to happen. Right? So conservative for a climate scientist is the opposite of conservative for an engineer. So we've managed to get over that. But really what we're doing is trying to much better understand each other's worlds. And so it means sitting down and talking together, learning about the language and the terms, and learning about the constraints that each has. So the other thing I've learned about engineers is, not surprisingly, and please don't feel offended if you're engineers, but they like to design to a specific number. And so they ask climate scientists for a specific number, and we infuriate them by saying, well, we can't give you a specific number because we don't know, but we can give you a range. But we're not sure it's even going to be in this range. It might be higher or lower than that range. So good luck with that. And so, one of the places we're getting, and this has really been driven home to me by my colleague Paul Kirshen, is that we have to think about designing for flexibility. It requires a different way to design so that as we get better information, we can change that structure. There's also sort of a whole series of no regrets, like putting all your utility stuff on the roof, right, in a place that's flood prone. But I think the answer to your question is it just takes time to collaborate and to much better understand. And none of us tend to have the time or the energy for that. And once again, as academics or engineering consultants, we're not really rewarded for that because it's a very long-term effort. But one, if we're really interested in solving it, we need to invest up front in understanding how other disciplines work.
I think that's all we have time for. Thanks again, Cameron.